the frequency is determined by mainly the beta network. So the circuit elements within that beta network is responsible for that frequency. So you have to be very, when you are considering the frequency, then you have to look into the beta network. So if the beta network is made of R and C, then it cannot generate high frequency signal. There is a limitation because the capacitor and inductor value, capacitor and resistance values that you can make, that actually restrict the frequency of oscillation at the output low frequency of the audible frequency less than 1 megahertz. Those class of circuit which is called the RC oscillator cannot generate. RC means the beta network is composed of with resistance and capacitances. That oscillator circuit cannot generate high frequency, that means greater than 1 megahertz. To generate high frequency, you need to choose those circuit elements. You know the circuit elements, okay? The basic circuit elements, passive circuit elements, you know, the resistor, inductor, and capacitor. The inductor and capacitor value, you can make it very small. The size of the inductor or capacitor as well as the value, you can make it very small. Okay, that is why this, if you construct a oscillator circuit where the beta network contains inductor and capacitor, that can generate very high frequency greater than 1 megahertz, or the radio frequency can be generated up to 1 gigahertz or several gigahertz nowadays is achievable with the help of a transistor. So that class of circuit is known as LC oscillator. That means the beta network contains inductor and capacitor. You will see inductor and capacitor in the beta network. No resistance is there. Resistance value cannot be minimized to a very small value. If you try to build a resistance for 0.1 or 0.01 ohm, that does not that is meaningless, because you know that type of resistance cannot be built. It is very difficult to build, and that resistance is close to zero. So that is why this RC circuit cannot generate very high frequency signal. We have discussed a Colpite oscillator circuit, and last day we have discussed this Colpite oscillator circuit. This Colpite oscillator circuit, you know this thing. We have discussed this one. Let me discuss it slightly, that very quickly, because the next oscillator circuit, the next oscillator circuit will be based on this, a slight modification of this Colpite oscillator circuit. So we just a slight repetition of the earlier class, that what is this Colpite oscillator circuit. You see that every oscillator has the amplifier as well as the feedback network. It's not it. So we have, you know that this is the amplifier section. This is the amplifier section. So this is your amplifier A. So this is your amplifier A. And you know this amplifier, it is a small signal CE amplifier, where this is R1, this is R2, and this is, instead of RC, you have R3, and this is RE. Instead of RE, it is R4, and this is the bypass capacitor, and these are the C3 and C5 is the blocking capacitor. So this is the basic constructions of the self-bias class A CE amplifier. So this purpose of this amplifier is to amplify the signal at the output. Okay. Now let us discuss the beta network. So at the output of the amplifier, you have the at the output of the amplifier, you have the output voltage V out. At the output of the amplifier, you have the output voltage. Now this output voltage is tapped here. So a part of the beta network input is tapping the output signal here, and at this point, it is producing some feedback signal which is going to the input of the amplifier signal. So this is the input of the amplifier, and in that the beta network output, which is the feedback signal, is connected to the input side. So in this way, the beta network is connected, and this is the beta network. Okay, so this is your beta. This is your beta network.
Sir.
Yeah.
Sir, John, okay.
So that is your beta network, and okay. So that is your beta network. So this is your beta network. I have just discussed that this is the beta network, and the input of the beta network is the output of that amplifier, and the output of the beta network, which is the feedback voltage, that is the input. At this point, you know that this is the input of the signal, and the feedback is connected to there. But look into the beta network. It is a inductor and C1, C2 capacitor are in series. So this is the constructions of the beta network, and the middle of the C1, C2 is connected to ground. So this is the construction, and we have discussed that how the phase shift condition of the oscillator, that means 360-degree condition around the loop of this A beta network loop is satisfied, because when the signal travel through the amplifier, you have 180-degree phase shift will be there, because you know that if the input signal at the input of the amplifier is like this, then the C amplifier actually amplify in the opposite fashion. So there is your 180-degree phase shift by the amplifier. And when this output voltage is tapped by the beta network, a fraction of that output voltage will be at the output of this beta network, that is the feedback voltage. And this is your feedback voltage. A fraction of the output voltage is connected here, generated by the beta network, which is when the signal travels through this beta network, again a 180-degree phase shift will be there. And that 180-degree phase shift actually makes this signal, again reverses this signal to this one. So 360-degree phase shift is, you are getting like this. And you see that this signal is again the input of the amplifier. So the feedback signal is again the input of the amplifier. So in this way, your 360-degree phase shift of the positive feedback condition is satisfied in this amplifier circuit. And also we have seen that the voltage across the output voltage and the feedback voltage, how they generate actually. Just a minute. Also we have seen that how this feedback voltage have been generated into the circuit. So this is the output point, and this is the ground point. So how to measure the output point? With respect to this ground, you are measuring the output. Okay. And again, the feedback voltage, which is this point potential. So feedback voltage, you have to measure this feedback voltage again with respect to this ground. So you are measuring this feedback voltage with respect to ground, and you see that this is the output voltage with respect to ground to the output point, and you can call this as a VO or V out. Then that entire voltage, this output voltage is developed across C1, C2. You see that this is the output terminal, and this is the ground terminal. So across C2, you have the entire output voltage across C2. And the feedback voltage, you see that feedback voltage is here. This is your feedback voltage. Okay. So this is the feedback voltage at this point or at this point. With respect to ground, this is your feedback voltage. So across C2, you have the entire output voltage. Across C1, the entire feedback voltage is developed. Or you can say that whatever is the voltage generated across C1 with respect to ground, that is feedback to the input side of the amplifier. So this is the way that the output voltage and feedback voltage actually develops across C2 and C1. And also we have analyzed this circuit little bit. How to analyze this circuit? We have analyzed this circuit like this one, that if we analyze this circuit, this tank circuit only, how we have analyzed this one last day, just to show you that how we have analyzed this circuit, that we have taken a current into the feedback into this loop. That means that within this beta network, we have taken a current like this. So if we assume a current flowing through this beta network like this, then the current actually, the magnitude of the current is I. Then this current actually flows through the C2, and that will produce a voltage across C2 in this direction. That is, the plus will be this side and minus will be this side. Okay, so this is the direction of the polarity. When the current I passes through this capacitor C2, it will generate plus minus here, and you know that the voltage across the capacitor C2 is also the output voltage. So what is the voltage across C2? That is the output voltage V0, and that can be calculated in terms of current I. So this is the current. We have shown that this is the current. So in terms of the current I, we can also calculate the voltage V0. So V0 equal to current I into impedance of C2, X C2. Suppose the reactance of the C2 is X C2, then the V0 can be equated to current I into impedance of the capacitor C2. Is that okay? Okay. Then same current I also flows through the capacitor C1 and produces a voltage. The polarity will be like this. So this side will be plus. Okay, this side will be plus, and this side will be minus. This voltage developed across C1 due to the current flowing through this. So this is the current actually flowing into the loop, and that current, this is the current flowing into the loop, and that current actually generates, it also passes through the capacitor C1. That actually produces a voltage across the capacitor, and you know that voltage across capacitor C1 is the feedback voltage VF. So this is your VF. So we have we can calculate the feedback voltage, what is actually feedback to the input side. That is the VF, that is the voltage developed across capacitor C1, and that can be calculated in terms of current, and that is your I into impedance of the capacitor C1. That means XC1 or 1 by j omega C1. So we have calculated the voltage V0 and voltage VA with respect to the current. And if you can remember this, if you take the ratio of these two voltages, so I into impedance of C1, XC1, and I into impedance of C2, then you will get the beta, which is a V0 by VF by V0 will become C2 by C1. So this was the calculation. This is a very simple way we have calculated that one. And also you can understand that how the phase shift actually changes in this case, how the phase shift actually, how the beta network actually shift the phase when the signal travels through this beta network, how the phase is actually 180 degree phase shifted. That means if the output voltage is here, is this one. So this is your output voltage, which is the input of the feedback voltage. Now at the output of this beta network, that is the feedback voltage, will be reversed. So you see that the output voltage is reversed when the feedback voltage appeared. You see the feedback voltage. This is the feedback voltage, which is just the reversal of the output voltage, this one, because there is a 180 degree phase shift when the signal travels to the beta network. So how this is happening, you can see, take a closer look into the voltage polarities across the C2 and C1. Across C2, you have the voltage, output voltage. This is the output voltage across C2, and the polarity is this side. Plus is this side, minus is this side. So with respect to the ground, this point is output voltage, plus is this side. Now what is the feedback voltage? That is the voltage developed across C1. And you see that the feedback voltage polarity should be like this, plus this side and minus this side. So with respect to this ground, this feedback voltage is minus, that is opposite. With respect to the ground, output voltage is plus, polarity is plus. Now you are measuring the feedback voltage with respect to ground, and the minus comes first. So it is 180 degree phase shifted. That is why this signal, which output signal, which is this one, this is the output signal and comes as a feedback signal. There is a 180 degree phase shift. So this is the principles you can explain, that how this beta network shift the phase by 180 degree. Okay, I hope that you have understood this one. And this actually gives you the idea that how the another 180 degree phase shift is generated at that point. And also you have calculated the beta. Beta is VF by V0. In terms of current, we can calculate this beta fraction. And in the book also, this beta fraction have been calculated. How this beta fraction have been calculated, you can very easily calculate that one. So you see that here. This is the calculation. So the beta, just a second. So whatever is the beta, just a second. Okay. So whatever is the beta, so this is your beta. It is represented as B in this case, but it is beta. You can consider this also as a beta. Okay. So this is beta. Beta is just the ratio of VA by Vout. And what is VA? Voltage developed across capacitor C1 due to the current flowing through the C1. That is the current I is flowing through the C1. That will be the current multiplied by the capacitance impedance XC1. And output voltage, what is your output voltage? Output voltage is the current I flowing through the capacitor C2 producing some voltage. So it is the current I and multiplied by the impedance of the capacitor XC2. So this is just in that way, by assuming a current flowing through the beta network loop, you can calculate the VA by Vout. So these two current in the numerator and denominator actually cancels out. So you will get XC1 divided by XC2. What is XC1? Impedance of the capacitor C1. It is 1 by 2 pi F R. FR is the frequency. Actually, R responsible for the resonant frequency. So 1 by 2 pi FRC1, this one, which is the impedance of the capacitor, and the denominator, you have the impedance of the capacitor C2. So ultimately you will get from this expression, you will get this one. So what is your beta? So ultimately the beta will become like this. It is C2 by C1 ratio. Okay. So from a very simple idea, this calculation is very simple. If you consider other books, there is a hybrid equivalent model of placed in instead of a transistor. There is a large calculation have been done into those books, and ultimately they got this expression. But this book actually very conceptually, within a very short conceptual discussion, it actually calculates the beta. So this is your beta, which is C2 by C1. That is the feedback ratio, beta equal to C2 by C1. So in that way, we can very easily calculate this beta. Then we can set, so we know that there is an amplifier whose gain is A. So there is an amplifier whose gain is A. So this is your A of the amplifier. And we know that there is a feedback network and the oscillation is going on. So A beta should be equal to 1. So this is the condition for sustained oscillation. That is, when a constant oscillation is produced by the circuit, then A beta should be equal to 1. But we have just seen, we have just calculated that B equal to, what we have calculated, that B equal to C2 by C1. Then what should be the value of A from this sustained oscillation condition? A should be C1 by C2. From this, you can easily understand that this should be the value of A. That is the how much the gain of the amplifier should be in case of sustained oscillation. To sustain the oscillation, what will be the amplifier gain? It will be C1 by C2 after calculating beta equal to C2 by C1. So in this way, we can very easily calculate this A and beta, how much will be for the sustained oscillation condition. Then one can very easily say that if we have a startup condition, how to start the oscillation. Initially, you know that if you want to start a oscillation, that means when you have to set the condition of the circuit, you have to design the circuit in such a manner that noise in the circuit can grow. If you put A beta equal to 1, noise cannot grow. Each time it travels, it will be multiplied by 1. So noise cannot grow up, because the noise will remain same. If you put A beta equal to 1, you will not get any signal. So to get some signal to start the oscillation, initially you have to set A beta slightly greater than 1. Then if the noise signal travels, traverses through the loop, each traversal, it will grow because it is multiplied by a factor which is greater than 1. So to start the oscillation in Colpit oscillator, you have to set A slightly greater than C1 by C2. That will make, you know, the beta equal to C2 by C1. So that will make A beta slightly greater than 1. So initially you have to set this gain of the Colpit oscillator C slightly greater than C1 by C2. So these discussions I have made are last day's class. I have repeated it because the circuit we are going to discuss is just a modification of the Colpit oscillator, slight modification, because there are some defects into this circuit. We will discuss that one, and that will be eliminated in the circuit that is slightly modified with respect to this one, and that is called the clap oscillator. And let me remind you that what is the frequency, how to calculate the frequency. Frequency is determined by this tank circuit. And whatever is this tank circuit, you know from the AC analysis of the parallel circuit, that is the inductor and capacitor parallel circuit, you know that this circuit is a resonant circuit. It has a resonant frequency FR, and that resonant frequency equal to 1 by 2 pi CR. Okay, sorry, 1 by 2 pi LC, where C is the series combination of C1 and C2. From that, you can calculate the frequency of oscillation, how much its frequency is producing at the output of this signal. That is the resonant frequency of the tank circuit, and that frequency is generated here. What is that frequency? And we have calculated that. You can calculate it very easily. So this is your resonant frequency is written here. You can see that. So this is the resonant frequency FR. This is the resonant frequency FR equal to 1 by 2 pi root over LCT, where L is the inductance and CT is the total capacitance. That means the capacitance of this series combination of two capacitors C1 and C2. You know that if the capacitor C1 and C2 are in series, then their equivalent capacitance formula will be C1 C2 by C1 plus C2. You know from the high secondary that is the parallel resistance combination. Okay, so FR equal to 1 by 2 pi root over LCT, where CT is this one equivalent capacitance of these two capacitors. So that is your CT. So this is all we have discussed about the Colpit oscillator. That the Colpit oscillator is a high frequency oscillator. So you see this L, you check this frequency expression little bit, why it can generate very high frequency. You see that the frequency expression, it contains L, and denominator contains L and contains C. This inductor and capacitance, usually this inductor and capacitance value you can make very low. Okay, inductor value millihenry, that means 1 into 10 to the power minus 3 Henry is a very large inductor. Now you can understand that how much small you can make an inductor value. Inductor value microhenry is a very small, considered to be a small value. Millihenry is a large inductor. So inductor value you can go to up to 10 to the power minus 6 or 10 to the power minus 9. Okay, but in case of resistance, that is not possible. If you say the micro ohm, that is meaningless, because micro ohm is nothing. Okay, in terms of resistance, it does not produce any, it does not actually resist the current. So micro ohm or milli ohm does not satisfy for the resistances. But in case of inductor, in place of, if you replace the resistance by inductor, you can go beyond a very low value. That is millihenry 10 to the minus 3 or microhenry 10 to the minus 6 or more. Okay, and capacitor value also you can go to up to 10 to the minus 12, again less. So for this reason, you are putting some very low values here in the denominator. So what will be the frequency? If you see that the denominator contains a very low value, so the frequency can go to a very high value. So this is the reason because the inductor and capacitor by nature, the values can be lowered to a very low value. That is why this frequency of this oscillator, where the beta network composed of inductor and capacitor can generate very high frequency, which is not possible if the beta network contains a resistor, because the resistance values cannot go 1 ohm means it is almost zero resistance. Okay, so that is why fraction resistance is meaningless. So resistance value usually cannot go beyond very low value. That is why oscillator does not produce a very large frequency, high frequency signal. You have to replace the resistance by the inductor. Then you have to produce, your beta network should be inductor capacitor. Then it can generate a very high frequency. Have you understood these discussions? Is there any difficulty? Any question is there? Have you got the points, all the points, everybody?
Sir, one
Yes,
question.
sir. No questions.
Okay. Anybody has any doubt? You can ask.
Sir, one question, sir. Where is these basic colpits are used? Most probably.
Colpit oscillator such as a radio frequency oscillator. Mainly, it is you know that frequency. If FM, you have heard the FM and the FM channels. You know.
Yes, sir.
So that FM that is 100 megahertz or 193.8 or whatever is the frequencies are there, that can be generated by this type of circuit. This Colpit oscillator can generate that frequency. Okay. So usually a Colpit oscillator can be used as a FM generation, that frequency, or high frequency, more than that. Up to 1 gigahertz, 2 gigahertz, you can generate with the help of Colpit oscillator circuit. So actually the frequency applications is dependent on the frequencies, you know. Okay, so in case of FM you can build the FM transmitter with the help of this Colpit oscillator circuit, but there is some problem is that the Colpit oscillator circuit frequency stability is not good. So you have to switch into the crystal oscillator to get a very stable FM generation. This only you have, but the Colpit oscillator and the crystal oscillator are almost same, because only you have to replace this inductor by a crystal that will function as a equivalent of the inductor, but the stability of the frequency, that means the output will produce একদম dot 100 megahertz if you design for 100, if your crystal is 100 megahertz. So that is the only difference. That so similar type of circuit, which is not exactly the Colpit oscillator circuit, but instead of this, based on this circuit, you can construct a crystal oscillator circuit which is similar. But that's this type of circuit can be used in that. Not only FM, in case of FM, if you have a high frequency generation in any applications, usually the VLSI circuit, you can use this circuit. I have said that the only defect is the frequency stability is not good in case of this circuit, because there are certain concerns are there. But this circuit you can use as a FM or high frequency, any other high frequency applications, 100 megahertz or beyond 100 megahertz, you can use it. Have you got your point? Have you understood? One application I have said, FM, you can generate with this type of circuit. Okay?
Yes, sir.
Okay. Let us discuss that what is the defect of this circuit. So you have to very clearly understood that what is the defect of the circuit. Then we will now modify this circuit to a very stable oscillator circuit. We will rectify what are the defects hidden into this circuit that actually is responsible for not generating some stable frequency. If you see the frequency expression, see the frequency expression in this one. So frequency is 1 by 2 pi root over LCT. So it is dependent on the inductor, and two capacitors C1 and C2. So these three elements actually responsible for this frequency. That means how much is the frequency is producing at the output by this circuit, produced by the at the output by this circuit. That only depends on inductor this L, C1 and C2. According to the formula, it's not it. Whatever so far we have discussed, but we have discussed very ideally. That means we have not considered other concerns that will hamper this frequency operation. That is change this frequency. That means there are certain things we have to consider, certain phenomena or certain other circuit parameters that can interfere this frequency expression, or it can change the frequency. Not only this, only frequency is not only determined or not only dependent on this only three parameters L, C1 and C2. What we have discussed, that is the truly ideal case. We have not discussed the what are the other things can happen into this circuit. That these three only the frequency is not only dependent on these three parameters only. The frequency, when the circuit actually operates, the frequency can be affected by the transistor. How this is so? I don't know whether you have understanding of the transistor. Transistor, we will discuss a high frequency model of the transistor, where I will show you that the transistor is, you have two junction is there. You see that there are two junctions. So this is a NPN transistor. You know that this arrowhead is outward. So that is a NPN transistor. So what you have in the transistor, you have a NP junction, base emitter junction, and a NP, another base collector junction. These two junction is there into the transistor. And PN emitter base is this emitter and this this emitter and this base is just a PN junction. I don't know whether you have learned the device electronics or not. A junction, PN junction, if you consider the PN junction, suppose I'm just getting you a very simple idea that you have a PN junction here. Okay. So in the PN junction in the middle, suppose this is your P, so this is your P and this is your N. So in the middle you have the junction, but there is a depletion region will be formed across the junction automatically. So in the depletion region, you know, there are in the P side you have the negative charges across the depletion region, immobile acceptor ions are there, and in the N side of the junction you have the donor positive charges will be there. This is the space charge region or the depletion region. So here will be the positive charges are there. Okay. So this is the depletion region. In the middle, this depletion region will be formed. If you have a PN junction, you know this thing. Okay. Barrier potential will come into this region. So this is called the depletion region. But now you just see this this structure of the PN junction, of a particular PN junction. You just see this structure. Is not it something like that? That is the parallel plate capacitor. Something like that one, parallel plate capacitor. If you have a parallel plate capacitor, then what happens? So this is an example of a parallel plate capacitor, the symbol of a capacitor. What is a parallel plate capacitor? One plate contains the positive charges. If the upper plate contains the positive charges, then the lower plate will contain the negative charges. So this is the in this way the capacitive effect actually goes on into a capacitor, and this structure is something like that of a parallel plate capacitor. So there should be you see that. So these are the positive charges layer, and this is the negative charges layer. As if not as if. So certainly in across the junction, across the depletion region, you have a capacitive effect. So this PN junction does contains a capacitor across the junction. So this if you consider the equivalent circuit of this PN junction, you will find a capacitor at least, because there are some positive layers of charges and negative layer of charges across the junction. So there should be a capacitance. This capacitance is called the depletion capacitance or the diffusion capacitance, which is the junction capacitance of the PN junction. If you have a PN junction, whether it is in the transistor, whether it is in the diode, or whether it is in the any other device, if you have a junction, in the junction you have this depletion region. In that depletion region, you have this positive charge layer and negative charge layer. So there should be a capacitive effect. Have you understood the point? Have you understood, got this?
Yes, sir.
Okay, now you see that what happens when we consider that capacitance of the junction, PN junction. Okay, what happens to this transistor? So, so this is your junction capacitances plus charges are there. So what happens? So this is your base. This point is your base, and this point is your emitter. So this is your base emitter. Base is P. So base is P, and emitter is N. So here, in this portion, you have a base emitter junction. A PN junction is there. Okay. So this PN junction is nothing but this one. So this is the PN junction. This is the structure of any PN junction. So in this PN base emitter junction, PN junction, you have a depletion region like this one. So definitely between base and emitter, you have a equivalent, you have a capacitive effect. That means between base and emitter, you should have a capacitance across the junction. So between base and emitter, you have a capacitance. There is no doubt, because there is a junction, there is a charge, charge layer is there. So there should be a capacitance. So that is why, because there is a PN junction between base and emitter. So that is why you can consider that between base and emitter, you have a capacitance between base and emitter. If you very specifically see the circuit parameters of the transistor, definitely between base and emitter, you have a capacitance. You are considering the DC operation of the transistor, then this capacitor will be open circuit, because DC current cannot flow through the capacitor. But when you are considering the AC operation, then this capacitor comes into picture, because the capacitor can conduct AC current, and these oscillator circuits are high frequency oscillators. So in case of high frequency, 1 by j omega c will be very low. So this capacitor actually conducts some AC current. So that is why these capacitors comes into play in this type of circuit, oscillator circuit. So the main point is between base and emitter, you have a capacitor. I hope that you have understood that this junction, each junction actually has a electrical circuit element, that is the capacitor, due to the construction of the PN junction. So now see that if you consider that one, then how this tank circuit will be affected. Now let us see that how this tank circuit will be affected a little bit. So between base and emitter, you have a capacitor. So here you think that there is a capacitor is there. So this is a capacitor is present, because there is a PN junction between base and emitter. If we call this capacitor as between base and emitter as CBE, suppose this capacitor is called as C, B is the base, and E is the emitter. CBE is the junction capacitance between base and emitter. Now you see that this capacitor, this terminal is connected through this capacitor. Bypass capacitor comes to the ground terminal, because you know that for the AC operation, the bypass capacitor is short circuited. So this terminal of the capacitor comes to the ground point, and this terminal of the capacitor, okay, this terminal of the capacitor comes to the ground point. That means at this point, it is coming at this point. And the other terminal of the capacitor, that means this capacitor, comes through this C3, because for the AC operation, this C3 is short circuited. So this terminal actually comes through this C3, it is short circuited, comes to this point. So here. So basically you see that CBE, this capacitor, which is the junction capacitor between base and emitter, actually comes between ground and this point, feedback point, or this capacitor actually appears here. Between this, it appears parallel to C1. That CBE comes parallel to C1. That can affect the capacitor, because you know now, if you don't consider CBE, then the capacitor between this ground point and the feedback point is C1. If you consider this junction capacitance of between the base and emitter, now that capacitor will be modified. It is now the parallel combination of C1 and CBE, because the CBE capacitor actually coming here. So now the equivalent capacitor will be C1 in parallel with CB1, that means C1 plus CBE. So the capacitor C1 actually does not solely determine the frequency. If you very carefully investigate, then the base emitter junction capacitance CBE comes parallel to C1. So in this way, the transistor junction capacitances affect CBE, affects the capacitor C1, and that is why you have designed for C1, but it will be changed due to the junction capacitance CBE. So between this point, feedback point, and the ground point, your capacitance value is changing because of CBE, which is the junction capacitance of base and emitter. So your frequency formula, if you put actual, consider this one, then that will give you that frequency will change from the design value. Have you understood this one? Have you understood this one? Have you got this one?
স্যার এটা আরেকবার বললে একটু ভালো হয় স্যার।
কেউ বুঝেছো? Anybody has understood this point? যদি না বুঝে থাকো রেসপন্স করো, তাহলে আমি ব্যাপারটা বুঝতে পারবো যে বুঝেছো কিনা। সৌভিক বলছো? আচ্ছা সৌভিক, এরপরে ক্লাস আছে? আচ্ছা ঠিক আছে। আচ্ছা, পিএন জাংশনের অ্যাক্রসে যে ক্যাপাসিটেন্স থাকে সেটা বুঝতে পেরেছো সবাই? Have you understood that the depletion region should have a capacitance of a PN junction?
Yes sir.
So if that is so, যদি পিএন জাংশনের অ্যাক্রসে ক্যাপাসিটেন্স থাকে, কারণ আমি তো দেখালাম যে ওর ডিপ্লিশন রিজিয়নে দুটো চার্জ লেয়ার থাকে যেন প্যারালাল প্লেট ক্যাপাসিটরের মতো, তাহলে তোমার তো এখানে ডেফিনেটলি তোমার এই যে বেস আর এমিটার, এই যে ধরো এইটা তো বেস আর এইটা হচ্ছে এমিটার পয়েন্ট, তাহলে এইটা হচ্ছে এমিটার, এটা হচ্ছে বেস। এই বেস আর এমিটারের মধ্যে কি আছে? এই বেসটা তো হচ্ছে পি আর এমিটারটা হচ্ছে তো এন। তো এইখানে তো এই দুটো পয়েন্টের মধ্যে জাস্ট একটা পিএন জাংশন আছে, যার একটা টার্মিনাল হচ্ছে বেস আর আরেকটা টার্মিনাল হচ্ছে এমিটার, তাই তো? তাহলে ডেফিনেটলি এই বেস এমিটারের মধ্যে যে একটা পিএন জাংশন আছে তার একটা ডিপ্লিশন রিজিয়ন আছে। এইখানে যে জাংশনটা আছে সেখানে একটা ডিপ্লিশন রিজিয়ন আছে, তাহলে ওর ওই বেস আর এমিটারের মধ্যে ওই ডিপ্লিশন রিজিয়নটা থাকার জন্য একটা ক্যাপাসিটর থাকবেই থাকবে, সেটাকে বলে জাংশন ক্যাপাসিটেন্স। কিন্তু ওর ভ্যালুগুলো খুব লো হয়। Usually the value of the capacitance is usually very low. Okay, তাহলে between base and emitter you have a capacitance here, so this capacitance is here. So between base and emitter you have a capacitance. This is called the junction capacitance of the transistor. Each and every junction of PN junction has a capacitance, and it is appearing the base emitter junction capacitance is coming here. because of the PN junction here. Up to this, is there any question? Have you understood that though we have not considered, if you carefully look the base emitter junction for high frequency operation, this capacitance appears because of the base and emitter junction, depletion region, there is charge layer, so there should be a capacitor. So between base terminal and between the emitter terminal, you have a capacitor which is connected between base and emitter. It is clear now? This capacitance
Yes,
base
sir.
emitter?
Yes, clear, sir.
So this capacitance value base emitter junction capacitance, you can call it as CBE. So this is the junction base emitter capacitance value. Okay, CBE. There is a capacitance. Now let us see that how this capacitance actually affect this C1. So between base and emitter, you have a capacitor. Okay, that there is no doubt that there is a capacitance. That is called the depletion capacitance or the junction capacitance of the transistor. So between base and emitter, you have a capacitance. Okay, the one end of this capacitance is connected at the base terminal here, but this capacitance for the AC operation, this input blocking capacitance is short circuited for the AC. It can easily pass through the short circuit, and capacitor actually performs only the AC operation. DC, in case of DC, all the capacitor will be open circuited. They does not take into part of the electrical activity for the DC. But when you are considering the AC, all these capacitors comes into play. And these C3, this blocking capacitor and the bypass capacitors are very high value capacitor for AC operation. That means at the oscillator frequency, these capacitors will be short circuited. So this path for the operating frequency operation is short circuited. So what happens? This terminal of the junction capacitance, which is for the base terminal, junction capacitance, base terminal, comes to this point through this short circuited C3. And this terminal, other terminal of that junction capacitance, which is the connected at E, that actually comes through the short circuited C4 to the ground. Because for the operation frequency of operation, this C4 is a high value capacitor that will be short circuited. So this is short for the AC operation. So this other end E, so this is comes here of the capacitor, and the other end terminal of the capacitor, which is the E terminal, comes at the ground level. So this is. So the entire capacitor, which is the junction capacitor between the base and the emitter, that entire capacitor actually comes across C1. So entire capacitor actually coming across this C1, you see that whatever is the junction capacitance, that is actually coming parallel to C1 between ground, which is the emitter, and the other terminal, which is the base terminal. So entire junction capacitance actually come across the C1. That CBE junction capacitance, when the circuit operates for the AC, it actually appears parallel to the C1. So you have designed the oscillator circuit for a particular value of C1, suppose 0.1 microfarad you have designed for the circuit, but the actual capacitance between this feedback point and the ground point will be 0.1 microfarad together with this junction capacitance CBE. That is the actual value connected between ground and feedback point. So your formula, in the formula, if you put 0.1 microfarad, that will be error, because the actual capacitance between that two points is parallel combination of C1 and CBE. That CBE you have not connected, but it actually comes due to the base emitter junction. There is a capacitor inherent within the transistor base emitter. So that actually gives you, if you consider that capacitance, that actually gives you the actual capacitor value, which is what should be the actual capacitor's value of C1, that is C1 in parallel with CBE. Then you can calculate, if you put this actual value, then you will get the correct frequency formula. Have you got this one? Now, have you understood this one now? Is there any confusion to anybody now? বুঝেছো নাকি বোঝনি? আর কেউ বুঝতে অসুবিধা হয়েছে কারোর আর?
না স্যার না।
তাহলে whatever is the tank circuit or the LC circuit, you have designed for a particular value of C1, but when you connect the circuit, when the circuit actually generates the AC signal, you will see that your design frequency at the output will not be same, because it is actually affected by this base emitter junction capacitance. C1 will be affected by this base emitter junction capacitance. Similarly, C2 will be affected. Similarly, in a similar way, the C2 capacitance will be affected. Why these two capacitors are affecting? Because the one end of these two capacitors is connected to ground. So with respect to ground, there all that stray capacitances actually appears parallel to this C1 and C2. That is why this capacitance C1 and C2 will be affected by the junction capacitances. Now we will understand how C2 will be affected. We have seen C1 is affected by the base emitter junction capacitance CBE. Now we will see that how this C2 capacitance will be affected by the transistor. You see, this is the collector of the transistor. So this is your collector of the transistor, and this is your emitter of the transistor. So between collector and emitter, you have two PN junction between collector and emitter. So base collector junction, PN junction, and base emitter, PN junction. As a whole, between collector and emitter, you have two PN junctions. So you definitely have another stray capacitance between collector and emitter. So between collector and emitter, there is some stray capacitance is there, and that capacitance is called as a collector emitter capacitance, stray junction capacitance. So this capacitance C is actually the collector and emitter capacitance, CCE. Capacitance between collector and emitter. So that is CCE. Now this capacitance is connected to the collector. So that means one end of the capacitor is connected to the collector. So this end is connected to the collector. Or in other way, this collector is actually connected here. You see the collector is connected here. So this end of the capacitor is coming here. The other end of the capacitor, so this is the other end of the capacitor, other plate or the other end of the capacitor, which is connected to the emitter. Now, you know that for the AC operation, this C4 will be short circuited. So this end is actually connected to ground because of the short circuited C4. So other end of that capacitor actually coming to the ground, that is at this point. So this CCE, which is the junction capacitance between collector and emitter, stray capacitance, actually becomes parallel to C2. So there you see there is a parallel capacitor, which is the junction capacitor between the collector and emitter, comes in parallel with C2 here. So in this way, instead of only C2, you have another capacitor is coming here. Instead of only C2, that is the junction capacitance between collector and emitter. That capacitance appears parallel to the C2, similar, just the similar way, just as the C1 capacitor is affected. So instead of C2, now you have another stray capacitance is here in parallel with C2. That stray capacitance is CCE, that is the capacitance between the collector and emitter. So this capacitance is due to the junction capacitance of the transistor between collector and emitter. So this C2 external capacitor, designed external capacitor, which you have connected to the circuit, will now be affected by the transistor junction capacitance when the circuit actually runs. So between this point, ground, and this point, output point, instead of the external capacitor C2, actual capacitance is the parallel combination of this C2 and this stray capacitance of collector emitter junction capacitance. This CE. So this is the capacitance which is coming from the collector emitter junction, appears across the parallel to the C2. So both the capacitance C1 and C2 in this way is affected by the transistor junction capacitances. Okay, the capacitor C1 is affected by the base emitter junction capacitance. So there will be a base emitter junction capacitance which appear when the circuit run, and transistor C2 will be affected by the collector emitter junction capacitances. So you have to consider these capacitances, otherwise you cannot calculate the output frequency of the oscillator correctly. When you use the formula 1 by 2 pi root over LC, that C should consider these two stray capacitance or junction capacitances of the transistor. Then you will get your actual frequency expression. Or in other words, you can say that the frequency of oscillation of this circuit actually is affected. The frequency of oscillation of this circuit is affected by the junction capacitance of the transistor. So this transistor is a semiconductor devices. It has some junction, base emitter, base collector junction, and due to that there is some capacitances, and that junction stray capacitances actually affect the output frequency oscillation. Why they are coming into the play? Because they are coming into play because these two capacitance C1 and C2 are both, one end of this capacitor is connected to the ground. If the two capacitors C1 and C2 is not connected to ground, then this stray capacitance would not have affected these two capacitors C1, but they are connected to ground. This is the reason that as it is connected to ground, so this point terminal actually capacitance actually through this ground actually coming. What happened? Sorry, there is some. Okay. So automatic add is coming. Also, sorry for the interruption. This is the advanced version of now new type of Play Store app. They automatically control this one. Okay. So so this is the problem of this circuit, that the frequency, that is why the frequency will not be stable. This junction capacitances is not of definite value. It depends on the operating point of the transistor operation Q point, and it depends on the other electrical parameters. So this junction capacitance of the transistor can change. So that is why the frequency output of this oscillator is not stable. If you are designed for a particular value of frequency, but when you run the circuit, it can change to another value, and during the operation, it also can change. So that is the due to this reason, because the C1 and C2 capacitances are connected to the ground, and that is the reason that they are affected by the junction capacitances of the transistor, and that actually changes the frequency of oscillation. That is why this oscillator is not a stable oscillator. Have you got it? Have you understood? Is there any confusion?
Yes,
is there
sir.
any question? Is there any question? Is there? Is there any question? Any doubt is there? Anybody has can ask me, because we have to now rectify the problem. These three capacitors C3, C5, and C4, they are large value capacitors. So when the oscillation grows, these capacitors become short for the AC operation. These C1, C2 is a very small value capacitances. Okay, they does not become short for the frequency of operation. And as well as the junction capacitances, which is coming here. So these junction capacitances is also very small. So they does not short. Only those capacitances C3, C5, and C4 for the AC operations become short. So that is why this junction capacitance is actually coming across parallel across the C1 and C2, and that actually changes the frequency of operation of this circuit. So that is the reason that this oscillator circuit is not stable oscillator circuit. The frequency is not stable. It will be modified by the stay capacitances or the junction capacitances of the transistor. I hope that you have understood this one. Let us now modify this circuit slightly. That is called the clap oscillator. So this is the FET version of the Colpit oscillator circuit. You just see that everything is same. Only the biasing of FET is there. If you learn the biasing of the FET, only one resistance you can connect here, or you can connect another resistance here. But the basic circuit will be same. This is the FET version. You see that the FET is also a 3-terminal device. This is the gate, this is the drain, and this is the source, which is the equivalent of the base collector and emitter. So FET is also a 3-terminal devices which you can make an amplifier with the help of FET. So FET circuit can also, you can design a Colpit oscillator circuit with the help of FET, and that this is the equivalent circuit. So if you can learn the circuits with one 3-terminal device like the transistor, then you can understand the other 3-terminal devices circuits. So that is why I'm just focusing on the transistor circuits. If you can understand this transistor circuit very clearly, then you can understand any other 3-terminal device circuits. The circuit will be similar. Here you have an example that if you have a numerical value of the capacitances, this is the capacitance, this is the capacitance value. You see, note the capacitance value 0.1 microfarad. Micro means 10 to the minus 6. So how small this capacitor value can be, which is not possible for the resistance. And the inductor, you see the inductor is 50 millihenry. Milli means 10 to the minus 3. So that is why these type of circuits can produce a very high frequency, because the circuit elements, capacitor and inductor, can have a very low value. So there is an example. You should read this example such that you can have a design concept. Next, our discussion is the Colpit clap oscillator. Okay, the modification of Colpit oscillator circuit is the clap oscillator circuit. So this is the clap oscillator circuit, where that frequency is dependent on the transistor junction capacitances. Okay, that actually changes the frequency of oscillation, transistor junction capacitance. Now this clap oscillator circuit will slightly, almost remove that problem. The junction capacitance problem will be removed by this clap oscillator. What you have to do, just you have to modify the Colpit oscillator slightly. Everything is same, just you have to modify slightly, very slightly you have to modify. You see that this, again, you have the same amplifier here. So this is the amplifier section built with the cell by C amplifier, and this is the tank circuit or the beta network. But you have to slightly modify this beta network, very slightly. What is the modification? How they actually amplify, how the problem, junction capacitance problem is solved here. We will now discuss this one. So you have to see the tank circuit. So this is the tank circuit you see. You have the same C1 and C2 capacitor here, C1 and C2 capacitor here, which is connected middle of the two capacitor junction of the two capacitors is connected to the ground. So this is your ground point. And this is the inductor here. Now you have connected an extra capacitance in series with the inductance. So this C3 is the extra capacitance you have connected here. This is the only modification you need to eliminate that problem, which we have discussed in case of Colpit oscillator circuit. This extra capacitance C3 now you have connected, and this capacitance C3 will be slightly larger than C1, C2. Okay, now let us discuss that how the problem will be modified here. Okay, so what will be now the frequency of oscillation? What will be the expressions for the frequency of oscillation? If the tank circuit is like this, what will be the expressions for the frequency of oscillation? Now, instead of two capacitors C1 and C2, you have three capacitors in series. So these three capacitors, you see, they are in series. So these three capacitors are in series. They are all in series. So what will be the equivalent capacitor of these three capacitance? What will be the equivalent capacitance of these three series combinations of capacitance C1, C2, and C3? Can anybody say?
1 by C1 plus 1 by C2 plus 1 by C3.
Yes, that is correct. The equivalent capacitance 1 by C equivalent equal to 1 by C1 plus 1 by C2 plus 1 by C3. So that is, you know better than me from the high secondary. So, just a minute. Oh, calculation is above. Okay. So this is your equivalent capacity. It's not it. Just what you have said. Just a second. Some stray line is coming. Okay. Yeah. So this is your equivalent capacitance of that three capacitances connected. 1 by C1 plus 1 by C2 plus 1 by C3. That is the equivalent capacitance. Then what will be the frequency of oscillation? The frequency of oscillation should be, so your frequency of oscillation should be like this. So this is the frequency of oscillation formula. 1 by 2 pi root over L, that is the inductor. So this is the inductor. And this three capacitance equivalent capacitance CT, that is the frequency that oscillator, this clap oscillator actually generating. Where CT, this CT actually this one. That is the equivalent capacitance of C1, C2, and C3 in series. 1 by C1 plus 1 by C2 plus 1 by C3. So the frequency will be modified if you connect a extra capacitance C3 and that capacitor is connected in series with L. Now what you have to do, only thing you have to do is that, now you see the previously this capacitor junction C1 and C2 is connected to ground previously. As well as in this case also, in the clap oscillator also, this capacitance junction point is connected to ground. This point is connected to ground. That is why this stray capacitance of the transistors appears parallel to C1 and parallel to C2 and affect the frequency of oscillation. But this C3, look into the C3 connection. The C3 capacitor, this capacitor, one end is, no end of this capacitor is connected to the ground. Across the C3 is connected in the inductor branch and no end of this capacitor is connected to ground, directly connected to ground. That is why the stray capacitances of the transistor cannot become or come parallel to the C3. So this C3 will not be affected by the stray capacitances. This much you can understand from the construction of the, now you have introduced a new capacitor C3, which is not, no end of this capacitor is connected to the ground. So the stray capacitances which generates between the base or collector point with respect to ground cannot come parallel to this capacitor C3. So this capacitor is actually completely free from the stray capacitance effect. What you have to do, you have to just make this capacitor C3 smaller than this C1 and C2, much smaller than this C1 and C2. What you have to do, C3 capacitor value, you have to make very smaller than C1 and C2. Why it is so? Because still you have connected the capacitor C3 and it is not affected by the junction capacitance, but still the frequency of oscillation is dependent on this L, C3, C1 and C2. So these two capacitors C1 and C2, which is one end of this capacitor is connected to ground, is still actually determines the frequency, because the equivalent capacitance also contains C1 and C2. What you have to do now, you have to somehow in the frequency expression, you have to eliminate this C1 and C2, because these two capacitors C1 and C2 will definitely will be affected by the junction capacitor. So you have to make a arrangement such that in the frequency expression, this C1 and C2 does not will be there, does not comes into the frequency expression. Only the frequency expression contains L and C3, then this problem will be eliminated, because if the frequency expression contains C1 and C2, that expression will be always be affected by the junction capacitance of the transistor. So for this reason, you have to make this C3 very, very smaller than C1 and C2. Then what will happen? If you see the expression now, you know this formula structure in the higher secondary class. You have learned this one. That if you make C3 much smaller than C1 and C2, then you know this formula. So this term will be larger than these two terms, very, very larger than these two terms. If you make C3 very, very small than C1 and C2, then 1 by C1 and 1 by C2, you can neglect with respect to 1 by C3. And in that condition, your frequency of expression does not contain C1 and C2. So in that condition, what happens? This equivalent frequency expression, which is this one. So if you make this C3 very, very smaller than C1 and C2, so this term will cancel out. You can consider neglect these two terms with respect to 1 by C3 terms. So your equivalent capacitance will be just C3. So your expression, frequency expressions now will be approximately will be 1 by 2 pi root over LCT, where CT is equal to your C3 only. So your equivalent expressions of frequency now will become, approximate expressions of the frequency will now become 1 by 2 pi root over LC3. So this much of modification you have to do with the Colpit oscillator. You have to connect a extra capacitor C3 across in series with the L, and you know that no end of this C3 is connected to ground. So that capacitor will not be affected by the transistor junction capacitance. And also, if you choose C3 smaller than C1 and C2, then from these expressions, equivalent capacitance expression, you can see that the C1 term and 1 by C1 and 1 by C2, that is the effect of this C1 and C2 capacitor, you can neglect in the frequency expression. So the frequency expressions only depends on inductor and the total capacitance in terms of C3. So it will only depends on inductor and C3. It does not depend on C1 and C2. So the frequency of the clap oscillator is only determined by C3, not by C1 and C2, which is affected by the transistor junction capacitance. So this frequency. So now you can get a very stable frequency of oscillation, which is only controlled by this capacitor C3 under this condition, and that is why this clap oscillator circuit actually more stable than the Colpit oscillator circuit. So the frequency of operation of this circuit only depends on this capacitor. Though C1 and C2 is connected here, but in the frequency expression, they does not appear because you have chosen this C3 much smaller than C1, C2, and the frequency expression, this C1 and C2 capacitor, this C1 and C2 will not appear into the frequency expression. Only C3 will appear, and that is free from the stay capacitance effect. So the frequency of operation of the oscillator will not be affected by the stay capacitance of the transistor, and that actually eliminates this problem of the Colpit oscillator. Have you got clearly?
Yes, sir.
Is there any question? Anybody has any doubt? Anybody has any question, any doubt, anything else you can ask? It is all the discussions have been written here, but this discussion is necessary to understand whatever is written into the book, and how this what are the effect of the Colpit oscillator and how it can be eliminated by the clap oscillator by connecting an extra capacitance C3. So now you can easily understand. If you have understood this one, then you can easily understand that clap oscillator is much stable, can generate much stable frequency than the Colpit oscillator. Everybody has got this one? Is anybody has any doubt, any question is there?
স্যার বলছি কলপিটস অসিলেটরের থেকে এটার সুবিধা কি?
এতক্ষণ তো ওটাই বললাম, সুবিধা বলতে এর ফ্রিকোয়েন্সি অফ অসিলেশনটা খুব স্টেবল হবে। আগে কলপিট অসিলেটর ওই প্রবলেমটা তো এটা এলিমিনেটেড হয়ে গেল, ফ্রিকোয়েন্সি অফ অসিলেশনেরটা খুব স্টেবল হবে, তাই তো? বুঝতে পারছো তো? এটা বুঝেছো
হ্যাঁ।
কেন স্টেবল হবে? কেন স্টেবল হবে সেটা বুঝতে পেরেছো? কারণ এই
হ্যাঁ।
ট্রানজিস্টরের যে স্টে ক্যাপাসিট্যান্স সেটা এইটাকে আর এইটাকে এফেক্ট করতে পারে, কিন্তু এটাকে করতে পারবে না, এর কোনো এন্ডে গ্রাউন্ডে নেই। এবং ফ্রিকোয়েন্সি এক্সপ্রেশনটাকে আমরা কায়দা করে, আমরা ওই প্যারালাল ফর্মুলার নেচারটা আমরা জানি, ফ্রিকোয়েন্সি এক্সপ্রেশন আমরা কায়দা করে ওই C3টাকে একটু স্মল রেখে দিলাম C1 C2 থেকে অনেকটা, তাহলে ওই এক্সপ্রেশনে দেখো ওই C1 C2 থাকবে না। যদি না থাকে, যে দুটো ক্যাপাসিটার প্রবলেম করছিল, যে দুটো ক্যাপাসিটারকে ওই স্টে ক্যাপাসিটেন্স গুলো প্রবলেম করছিল ট্রানজিস্টরের, সে দুটো ফ্রিকোয়েন্সি এক্সপ্রেশনে নেই, শুধু C3টা আছে। তাহলে ওই স্টে ক্যাপাসিটেন্সের জন্য যে প্রবলেমটা হচ্ছিল, ফ্রিকোয়েন্সি চেঞ্জ হয়ে যাচ্ছিল, সেটা থাকবে না। শুধু একটা সার্কিট একটা ক্যাপাসিটার C3 দিয়ে ফ্রিকোয়েন্সি ডিটারমাইন্ড হবে, দুটো ক্যাপাসিটার দিয়ে তোমার ডিটারমাইন্ড হবে না। তাহলে ফ্রিকোয়েন্সিটা অনলি ডিটারমাইন্ড বাই অনলি ওয়ান ক্যাপাসিটার, দ্যাট ইজ C3। তাহলে তোমাকে একটা প্রিসাইজ ক্যাপাসিটার চুজ করতে হবে, আর তার ভ্যালুটাই C1 C2 থেকে অনেকটা কম রাখতে হবে। তাহলে তুমি খুব স্টেবল আউটপুট সিগন্যাল তুমি এখানে জেনারেট হবে। এখানে যে স্টেবল আউটপুট সিগন্যালটা জেনারেটেড হবে, এই আউটপুটে যে স্টেবল সিগন্যালটা ধরো তোমার জেনারেটেড হবে, সেই স্টেবল সিগন্যালটা এই যে টাইম পিরিয়ডটা, এই টাইম পিরিয়ডটা 1 ইনভার্স করলে তো ফ্রিকোয়েন্সি পাবে, সেটা এই ট্রানজিস্টরের ক্যাপাসিটর গুলো দিয়ে এফেক্টেড হবে না, চেঞ্জ হবে না, ওটা একদম স্টেবল থাকবে। এই হচ্ছে তোমার ক্ল্যাপ অসিলেটরের অ্যাডভান্টেজ। বুঝেছো?
ওকে স্যার।
আর কোনো কোশ্চেন ডাউট আছে? অসিলেটরের প্রবলেম হচ্ছে ফ্রিকোয়েন্সি শিফটিং, ফ্রিকোয়েন্সি শিফট করে যায়। মানে তুমি যেটা ডিজাইন করেছো, একটা পার্টিকুলার ধরো 100 মেগাহার্টজ তুমি ডিজাইন করেছো, কিন্তু 100 মেগাহার্টজ থেকে ও ফ্ল্যাকচুয়েট করতে থাকে। বুঝতে পেরেছো? তা তোমাকে সবসময় স্টেবল অসিলেটর বানাতে হবে, যাতে করে ও 100 মেগাহার্টজেই থাকে। আর কোনো কোশ্চেন আছে? আর কোনো ডাউট আছে কারুর? যদি ডাউট না থাকে তাও রেসপন্স করো, তাহলে আমি বুঝতে পারি।
না স্যার, ডাউট আর এরকম না।
ঠিক আছে, তাহলে এই দেখো, এই বইটা পেয়েছো তো? আশা করি সৌভিক সবাইকে শেয়ার করেছে। এই বইটা থেকে এগুলো পড়ে নাও, তাহলে যে ডিসকাশন গুলো হলো ওখানে লেখা আছে। আফটার দিস ডিসকাশন ইউ ক্যান আন্ডারস্ট্যান্ড ভেরি ক্লিয়ারলি। ওকে, আই হোপ সো যে আমি তোমাদেরকে ঠিকঠাক বোঝাতে পেরেছি। ওকে, আজকে তাহলে এই অবধি থাক, ঠিক আছে? নেক্সট ডে আরো দু একটা খুব স্টেবল অসিলেটর হচ্ছে ক্রিস্টাল অসিলেটর। অ্যাকচুয়ালি যে অ্যাপ্লিকেশন গুলো এফএম টেফএম ওই ক্রিস্টাল অসিলেটর ব্যবহার করে, সেটা আমরা পরে ক্রিস্টাল অসিলেটরটা পড়বো। আরেকটা অসিলেটর বাকি আছে, হার্টলে। ঠিক আছে, তাহলে আজকে এই অবধি থাক, পরের দিন আবার হবে। ওকে, ওকে।